Okay, good evening. This is February 12, 2024, Monday, and this lecture is recorded for our lecture in Chapter 8, the third lecture on Chapter 8. So let me bring up my lecture contents so that we can all go through that together. Now to section part 3. Actually, before I proceed, let me start share screen so that you can see what I'm talking about. This. Right, so in Chapter 8, in the first part, we talk about the current mirrors based on like mouse rats, and then we also talk about the different, in the part 2, we talk about the basic gain unit and how we actually build the different amplification basic unit. And those units are based on different load devices. For example, we talk about resistor load, RL, and we talk about current source load, and we also talk about occasionally how to increase the gain, how to increase the input impedance, and also how to decrease the output impedance. So one of the very important thing that we will be doing, in fact, is how do we increase the gain of a basic amplifier? Like typically, you already know the gain of a single like common source amplifier. So let me start maybe writing in some notes. So, so the simple like common for common source amplifiers, the gain is or the gain, that means is just typically like a GM times GM times VGE is a current and times RL, and then that is divided by VGE, VGS, and you can see that the gain is GM times RL. So what this GM is typically quite small. In the, for example, 20, a typical volume maybe 20 milliamp per volt, and RL could be say 5K. So in this case, you got a gain to be roughly 5K times 5K times 20, so forth. It's about 100. So not bad. And for common drain amplifier, we know that AV is approximately 1. And when the load resistance change, things start to change. So how do you increase the gain of a circuit? So here we have a quite interesting example, and we have amplifier at the bottom. You see the amplifier at the bottom? So at the drain, we have the output at the drain of Q1. So, but instead of taking the output of drain of Q1 at D1, a point at D1 on the graph, we actually instead, so yeah, I can draw another circuit here, so just that you have a comparison, the big differences. So in a typical, the single gain unit we had was like VDD with RD at the drain. And in this case, our drain is connected to ground for small signal. So your output is where we calculate for common source is here, is like we kept the gain. But here we replace the resistance with a kind of a current source. Of course, that G2, the Q2 can be considered as a current source, but there's also another current source, like as example, that we built from the current source that we discussed earlier in this chapter. So what we're doing is we can basically look at the drain circuit, and we can find what the total gain is for this circuit. In order to do that, we would need to derive the small signal circuit, and then we can look at the gain. So let me draw the small signal equivalent circuit so that we can clearly see what the gain is going to be. Before doing that, probably it's a good idea to erase some of the contents over here because this is not going to be very useful anyway. So I'm going to also erase this circuit over here, so we're not going to use it. We're going to draw the equivalent circuit of Q1 first. So Q1 has an input at the gate of Q1 relative to ground. And then we have, and then I'm using the pi model at this moment. Now I'm going to include RO1 of Q1. And we know that this is GM times VGS. Okay, so I'm finishing this Q1. And then I'm going to work on Q2. So for Q2, you can see that the Q2, the source of Q2 is connected to the drain of Q1. And the gate, VG2, is a DC voltage, so it's going to be a short circuit for the for AC signal. And the source is connected to as the output, and then there's also a constant current source at the drain. So we're going to neglect the current source over here. So we're going to draw the equivalent circuit of Q2. And then this is ground. And so the very important thing is that the current source at the top, which is for Q2, is going to be GM times VGS2. And because VG2 is grounded, and how do you, and the source is also connected to the drain of Q1. So you can see that the voltage from VG2 to the source of the drain of Q1 is VGS2. And then VGS1, of course, is our input, right? So let's make sure that I want to, that's not connected. I just want to make sure it's not connected. So VG2, so that's VGS1. So you can see here, if we calculate VGS2, that's going to be equal to 0 minus Vs. Right? So 0 is VG2, is grounded. Vs2 or equal to 0 minus VD1. You can see here is VD1. And VD1 is what we look for is actually, in this particular example, we are looking at the output is between D1 and D2. So that's VO. So what is VD1? VD1 relative to ground is, if we look at the current source here, I can redraw the circuit just to make it a little bit better, so that make it a little bit here. So we'll make it, so that's Q, and that's Q1. So we can see that basically we can get VD1 is equal to the current through this, which is GM1 times VGS1 times R0, and then give it a minus sign. So that's VD1. And VD1 is equal to VGS2. So now we can plug in this. In fact, let me also erase this because that doesn't really have anything else. Okay, so we got VD1, then we got a VGS2 is minus VD1. So now let's calculate VD2. So we calculate VD2 now. So VD2 is going to be VD1 plus, or in this case, in fact, it's going to be not plus. So we're going to have, because the current, oops. The current here is actually up. So ID2 is this way, which is equal to GM times VGS2. So we'll have VO, or VD2 is defined over here. So VD2 will be the voltage across RO2 over here, RO2, plus the voltage at VD1. So because the current flowing down, so flowing up, so VD2 is actually negative GM VGS2 times RO2. That's the voltage, and then plus VD1. Okay, so that's how we got that that voltage. So VO now we can calculate it. VO is equal to as you can see from there, we got VD2 equal to GM blah blah, and then we have plugging in the VGS2, which is minus VD1, so we got VGM. Oh, hold on. This is relative to ground. And VGM times VG RO2 here. And we plug in VGS2, which is minus VD1, so positive. Now GM1, RO1, and then times VGS1. So there's a VGS1. So times VGS1. And then give me 1 second. I'm gonna think about what happened to there. So I was supposed to get VO equal to VD2 minus VD1 equal to minus GM1, GM2, RO1, RO2 times VG times VI. In this case, that's input, which VGS1 is VI. So, and then we can calculate the gain, which is voltage gain is VO over VI, which is minus GM1 RO1, let's substitute times GM2 RO2. And that you can see that's the gain 1, that's the gain 2. So if GM1 and GM2 is the same, if GM1 and GM2 is the same, RO1 and RO2 is the same, or if the transistors are identical, you will get the gain to be the square of a single gain. And so that's really is important. Now, what I think of what was a mistake I made a little earlier was that VD2 is relative to ground. It's not. See here is V is relative to ground. So that's important. Let me do this way. So VD2 is relative to ground is this much, and then VGS2 was solved, and VO, of course, now I need to correct this mistake also. So VD2 is so positive, yeah. So VO is equal to VD2. Okay, so that's what we get. Sorry about that. So VO is equal to VD2 equal to. So what we found is here, just I need to redraw the circuit, because if you look at circuit over here, really VO is defined relative to ground. It's not relative to VD2. So I'm probably going to erase this one here. Yeah. So VD2. Is relative to vertical, and this is a VD1. So this is how we got it. So now we get the gain. As you can see, by inserting another like identical amplifier or current source at the drain of the actual amplifier, we simply double the voltage gain of the circuit. So this is very significant. And we would simply needed to, so this circuit actually is much clearer than the previous circuit, which shows where the voltage is referenced to. So I'm just earlier I made a mistake. I thought the output was between D2 and D1, which is not, which is between D2 and D1. So we can just to recap what we did, refresh what you just learned here. We can redraw the circuit to further enhance our learning. Is this is your the RO1 is input here, and then we have so this is our VO relative to ground. So that's important. And this RO2, this is going to be GM times VGS2, and this is GM 1 times VGS1. This is RO1, this is RO2, this is GM2. And the most important thing is where is that G2 is connected. So this is VGS1. That is clear, equal to VI. But VG2 is relative, the VG2 is connected to ground. So that's the critical part. So between, as we mentioned earlier, so this is important to look at what VGS2 is. So VGS2 is really the voltage between gate and the source of Q2, but G2 is grounded. So right away, you can see that this is VD1. You can see that VGS2 equal to minus VD1. So that's the key thing that VD1. And then we have VD1 is calculated to be minus GM1 VGS1 times RO1. Right? So, and then you have VO equal to relative ground. So that's GM2 VGS2 times RO2. So, and also there should be a minus sign. And when you plug all this in, we got a VO equal to minus GM1 RO1 times GM2 RO2 times VI, and your A equal to GM1 RO1 times GM2 RO2. There's minus sign. So one identical mass, we have A equal to A squared, like A1. Each one of them is kind of a square. So that's really how I think, just to enhance the knowledge, I already did the equivalent circuit. That's all we did. But the question, of course, is that if the load is not ideal, like in the previous circuit, well, basically we had a current source over here, and we thought this is ideal. This is ideal current source. But if this is not ideal current source, if that Q2 up above Q2, there's another thing. And then this thing is going to start to change. So ideally, from the current mirror and the current source, we already derived that for any like current source. So here, we treat this one as part of the current source. If we remember how to draw the current source, which is kind of like this. Make sure I draw the same correctly. So for the current source, we often like have the circuit operate with the drain. So that's your current source, which like this is a Q3, and then we can call this like Q reference. So that's what you have with your current source, right? So the current source, this is the, I'm sorry, this is like the NMOS. But for PMOS, it's very similar. We can certainly draw the equivalent circuit, but for the time constraint one. But the idea is that this Q3 is in there for small signal, the current source is equivalent to like RO as kind of the load, the output resistance. Okay, so if we have that resistance to equivalent, so in this case, the equivalent circuit of this one can be drawn as, right now, you can be drawn as here. I'm going to redraw the circuit. So if you look at this one here, the Q1 is the same, and Q2 is going to be a ground for small signal, and Q2 is the same as before. But the only difference is that about Q2 initially, if you look at here, we have a current source in this example. But instead, we have here is what that current source apparently has an internal resistance. We have RO3 instead. So when you have RO3 instead, the voltage there is going to be totally different, because whatever that gain that we got before now is no longer going to be exactly what the same that we got. So we can derive, let me see, so we can, for simplicity, we can use equivalent circuit like this, because in this circuit, you also have this, like we neglected, which is VI is here. So VI is coming in, and we do the circuit, and we need to do is to look at the output resistance of Q1 and Q2, and also the load, like the input resistance of the output circuit. So by doing that, you can find the gain of this circuit. Now, if we know the gain of this circuit, like we can easily calculate the output VO is going to be GM times VI times RO in parallel with RL. And then there's going to be minus sign. And there's going to be a minus sign here. So VO equal to minus this. And then we can find the gain is going to be VO over VI. It's going to be minus GM. This is GM1 really. RO and RL in parallel. This is GM1. So for this case, we have the gain identified. However, we still have to figure out what RO is, what RL is, to get accurate value. This is partly addressed in our previous lecture, is to look at what is the value of input and output resistance. In this particular example, we will have IL equal to RO3, and we have RO equal to, let me see, 3. Let's see, find out the equation here. The equivalent circuit that we got is going to be in this case, we have, yes, so from the previous example, really, we can come here to use this equation here, because over here we got the AV, and this AV is equal to this, right? So, and also we know the equivalent circuit, we know the current source. So basically, I'm gonna rewrite the equation on this page here. So AV is equal to minus GM1 RO1 GM2 RO2 increase page. So which means VO is going to be AV times VI. And if we use and then the input current is going to be, let's see how we got the equivalent resistance. So basically, okay. So the equivalent circuit is going to look like this. That's what we draw. Sorry, we need to do this again. Just like RO. That's GM1 times VI. It's the current. So if we do this, we'll find that the resistance RO equal to VO over GM times VI. So this is RO. That's the equivalent resistance. That's the whole equivalent circuit. So everything here comes to this equivalent circuit, and VO is going to AV times VI, and then VI is going to cancel, and GM1 is going to cancel. So we got is GM2 times RO2, and then times RO1. So here we got RO. So we redivide RO, and then we go to this equation here. We got RO, and also we have RL. So RO is GM2 times RO2 times RO1. And RL is RO3. So one of the very important conclusion we can make is that because RO1 and RO2, RO3 are similar, so RO1, RO2, RO3 are similar in value because they are kind of similar MOSFETs that we use. Therefore, RO is much larger than RL because we're multiplying RO1, RO2, and then multiply by GM. So in this case, because RO is much larger than RO2, you can conclude that this A, we in this case, look at the bottom, it's GM1 times RO in parallel with RL. Because RL is much smaller than RO, so the parallel resistance is approximately RL. So this goes to GM1 times RL, which is RO3. So here you can kind of conclude, well, if you got the non-ideal MOSFET, like Q3 at the low resistance, your gain goes back. Instead of doubling, remember on the previous page, we have the gain, which over here is kind of the square of a single stage gain, a single amplifier gain. But once we got a load resistance over there, everything started to change. So, well, the question is, how do I increase the gain with non-ideal case? Well, this is very simple. So instead of doing a single RQ3 as a load over here, we're going to add another Q4. So similar to what we did Q4. So in this case, if you look at this PMOS, we can do the very same equivalent circuit, very same analysis. You'll find, well, the RO4 is the kind of the load resistance over here. And if you look at from Q3, the Q4 is a load of Q3 in this case. So from Q3 perspective, the resistance is going to, or the RO, let's call it RO PMOS, it's going to be GM3 RO3 times RO4. Remember, this is what we got from the previous one, the RO. Now, if we add N later on, that was GM2 RO2 times RO1. So if we add N over here, we get this is for the previous page. Okay, so with this, if we add this to the previous, so if this is from previous page, and we will get the equivalent circuit, let me see if yes, I do have that. So what we get is this equivalent circuit is now very simple. So this is your input, Vi, and your output equivalent circuit of that amplifier. This is your amplifier. With GM1 times Vi is the equivalent amplification, and you got RON, which is the load resistance of Q2 is Q2 between Q1 and Q2, so that's Q1 plus Q2. And here on the right hand, it's Q3 plus Q4. Now, Q3 and Q4 have equivalent resistance of ROP, as ROP. Now, you really, what you have, you can calculate VO is going to be minus GM1 times Vi times the resistance of RON in parallel with ROP. And your gain now is calculated. So your gain VO over VI equal to GM1 times R1 over ROT in parallel. And since if we select again identical or matched modes, and then we'll likely have RN equal to ROP. And then RO and ROP in parallel will be, if you still doubt, it's going to be RON squared times RON plus ROP, which is equivalent to 1/2 RON. So because RON and ROP is the same, let me just do this a bit. And when we plug this back into this gain, we got this gain to be, I forgot minus thing. So minus GM1 times 1/2. And then if we plug this RON back in, you'll find out that this A equal to 1/2 S squared. And this is very important. So by adding a PMOS pair as a load at the drain of the previous cascade amplifier, we now increase the gain by again square. So one magnitude of A, but a half. It's not exactly A squared, but it's a half of that. So but still, in the future, you might say, well, eventually, we are going to have a lot of resistance anyway. So eventually, it's not going to be, so that's why we want to have different options. So in this case, we can draw the equivalent circuit to be, from the previous page, we know that we can draw this instead of that ROP, we got RL together with O. So now you can calculate this VO equal to eventually the load is going to be, so we is equal to minus GM1 with I times the parallel RO over RL. But of course, the idea here is RL is much smaller than RO, and then your VO goes back. But if RL is equal to RO, and then you got A, so this one you got basically goes back to A1, and this goes to A squared half. And if RL is infinity, and this goes to A squared. So basically, in the book, there's a table, I believe it's a table 8.1. So it summarizes like different load, like amplifier. Like if we have, say, the different cases with load, we can summarize it here. So if you have case and you have load, well, there's some other things you can list in table, but the case is if RL changes, and your resistance will change. So in the first case, if RL is infinity, we got this A is A squared. And if RL is ROP, then we got this 1/2 S squared. And if this RL is is simply like a load resistance is like a very small, and then it just goes back to really just A. Just A. So you can review the book and then you get a different results of this case. Now in cascade amplifier, not only we have MOSFET, we can also use BJTs to build so this is the equivalent circuit. We can also use BJT to build the cascade amplifier. So for simplicity, we're not going to really draw the very complicated equivalent circuit to solve the IC, KCL, things like that. But in this case, we'll simply draw the equivalent circuit based on the output and input impedance. So the idea is this: if we draw the input, and this R pi 1, and this is your input, PI, and then this is grounded. This is going to be GM1 VI, okay, and this has this RO is the internal resistance. But you remember the output in this particular circuit is that VB2 instead of VB1, right? So this instead of VC1. So VC1 is here, but VC1 is connected to VE2 of that circuit. So for this circuit, we have VB2 is going to be grounded. And the current over here, this R pi 2, this current here is the current of the amplification current of Q2 is going to be GM times VBE2. So the most important thing here is really to identify what is VBE2. And by definition, VBE2 is here. Maybe it's better to do it this way to make it a little bigger. So I'll make this a little bigger so that it's easier to see. So this is a B, this R pi 2. VBE2. So the most important thing is to calculate VBE2. So VBE2, I write it here. So VBE2 equal to minus VC1. You look at VBE2 is minus VC1, and VC1 is equal to VC1 is equal to minus GM, so this becomes positive. GM1 VI times RO1. So that's where you get this VBE2. And when you plug this VBE2 into the gain here, so we get a VO equal to minus GM times VBE2 times RO2. And then we're plugging VBE2 here. We got this is GM2. Sorry, I got GM2. So in the minus GM2 RO2 times GM1 RO1 times VI. So the gain is easy to calculate. There's not much difference. But the only thing is that when we calculated this VC1, we used the current. We assumed here the current here. We assume the current here is going to be 0, but in fact, that current at the here is not going to be 0. So because if that current is not 0, and there's current here, and this current here, right? So we need to just to be careful how to calculate those. So when you consider all those coming in, basically you have a little bit different gain, but in this case, we neglected that current, so we got the gain. So since we got the gain over here, and we control the equivalent circuit, and this equivalent circuit has RO. So based on here, we can calculate RO equal to VO over GM1 times VI, which is the current. That gives you it should be minus VO divided by this, so then we can get rid of the minus sign. Well, no, actually, no. In fact, minus minus sign. So this is actually positive. Okay, just no minus sign. Let me erase this. This is positive. Okay, so this is going to give us GM2 is going to GM1 is going to cancel, and VI is going to cancel. So we got GM2 RO2 times RO1. So that's the equivalent resistance. So by this time, you probably already clear that given the equivalent circuit, our gain is very big. Our gain is like, again, the gain here is A1 simple squared, right? So we can view this one, so A equal to A1 squared. So this is very useful. But you might already think, okay, well, what happens if that current source is not ideal? So that will go back to the 3 transistor case as a MOSFET. And then what happens? So in that case, it will bring the gain much smaller because RO3 is going to be that, right? So ideally, we want to simulate what we can do with the multiple transistors with the PMOS at the top as a load device. So in this case, you can basically redraw the circuit to like what we did similar before. So you have input with I, and you have R pi 1 input coming here, and you have this, and you have this. Let me draw this, and this your VO, and you have RO, again PMOS, and you have RO NMOS, and the gain here is going to be GM times VI. So for this example, you have your AV is going to be minus GM1, this GM1, times RON in parallel with ROP, which is exactly identical equation as you get for a MOSFET. So if MOS are identical, you get AV equal to minus GM1 times 1/2 RN, which is which is 1/2 A squared. So that's exactly what we get as a in the MOSFET case, right? So I want to spend just a little bit of time also to talk about the source follower that we had, the example for the source follower that we had in the by the end of chapter 9, in early beginning of chapter 8, I reviewed the source follower where we have a resistance at the load. But apparently, you will see more and more that instead of using resistance to bias the circuit, we use a lot more current source. So in this case, we have amplifier over here, and then we have the pair at the bottom here as the current source. And here is your amplifier. The top is your amplifier. So the equivalent circuit of this can be redrawn as So simply like well, for the DC case, probably we should draw the VDD. And so this is equivalent of this current source, so IO. So when you have this circuit, what we wanted to do, now the output is over here, right? So if IO is the idea, and then the source becomes open circuit, and so we have to have some sort of load at the output, to get the output. Otherwise, the circuit will not work. But if IO is not idea, you will have some sort of resistance connected. So in this case, what we are doing is we are really adding RO here, but that RO apparently is equivalent to RO3, which is a resistance of Q3. That's exactly what we got from the previous, a couple of examples before, is that current source equivalent resistance RO3. So eventually, you will have this equivalent circuit. So we can draw the equivalent circuit now. Again, you can use the pi model or T model. We can do both. So with a pi model, we have this, and then we have this. So here you can see the current that is flowing here is Gm times Vi. And suppose the VO is connected to nothing, you will easily get VO equal to Gm times Vi times RO3 times RO3. This is positive. And your gain can be calculated as VOOVI equal to Gm times RO3. It depends on the value of RO3. This gain can be typically quite small. So in the book, we have redraw the whole circuit that includes also RO1. So when you include RO1, it's a little bit different. So we can derive that over there, and well, actually, no, I'm sorry, there was a mistake here. No, that's wrong. Because when I draw the circuit, when I redraw the circuit, that I forgot that VGS is not Vi. So again, so this is very important. So VGS is not equal to Vi. So if VGS is not equal to Vi, that's where the trouble comes from. So we draw this one. That's the key. So Vi is relative to ground. Vi is relative to. And here we have O. And VGS is here. VGS. Okay. So this here. And depending on what VDD is connected, and we might have other things connected as well, we can, for now, we can neglect this part. So we will simply connect this to ground. So based on this, it's a little bit like difficult to really get the So a little bit difficult to get actually the equivalent, the output, because you can see here, you look at the bottom, well, we have VO is defined at VO is defined over here. What we can do is we can certainly write node equation around this node over here. And then here we need to be careful is VGS is not VI. So if you look at VI in this example, VI equal to VGS plus VO. I think that's important that we get here. And then we can write node equation based on that node. It's VO divided by RO3. This is RO3 plus, that's current going out, plus VO over RO1. That's current coming out, equal to current coming in is GM times VGS. And then plus there's another current. Current, forget about this current. You can really ignore this current over here. So no current here. So by plugging VGS to here, we replace that with VI. So from here we can get VO. I'm going to neglect all the steps to derive the actual gain. The actual gain is going to be let me see how much gain is going to be. Well, without considering the actual, like the current source, that's equivalent of the other stuff there, but we can get eventually we can get the input and output resistance and also the gain. Let me show you the actual gain is going to be roughly gain is going to be oops. The gain is going to be we I is going to be I L over that's what we get. And so previously, we had the cascade amplifier, and it also has a current source. So in this example, we are going to look at a slightly different current source or current mirror in other sense. How to increase the output or the input resistance of the current source, which is served as a load resistance for the amplifier. So in this example, I think we have 3 things to cover, but probably we are running out of time. But let's look at this current mirror with 2 things in series, with Q1, Q4 in series. So this example, you can see that the VGS1 equal to VGS2. So therefore, IQ1 is going to be IQ2. Let's use IDQ1, IDQ2, right? Because VGS is the same. And we assume all them in saturation mode. And VGS4 and VGS3, then we didn't say it's the same because the source of them is not connected, right? So the source is not connected. So this VGS over here, not necessarily same as VGS over here. However, because the current is the same, so basically you can eventually conclude that, well, they got to be the same. Otherwise, you're not going to get the actual result. So the question is, why would you do this? Well, the idea is that we got this RO is really here is going to be what we got from before is GM3 times RO3 times RO2. Because this increased the output resistance, therefore we can use them as a load, so that if we use this as a load, you can increase your gain, dramatically increase your gain. So this is what we call a cascade current mirror. The idea is that to add one more stage on the current applied to increase the output resistance of the circuit. And based on the same principle, we can do also the current mirror based on the BJT, right? So, and then with BJT, of course, a little bit complex because the current is no longer zero at the base. So that's where the difference would come in. So I think we're going to spend a little bit more time next week to talk about Wilson and also the Wilder current source. They are very simple current sources. For example, we can do both, and we're going to do example based on. We're going to do a few examples before we conclude the chapter 8. Okay. So with that, I think I'm going to stop here. So it's a little bit. Actually, in fact, let me do this example first before we get to conclude the class. I'm going to leave the Weldon and the Wilson current mirror and the Wilder current source to the next lecture. So, but let me do this example. The last example, 815. So this is a very important example that we do. So in this example, the voltage on the top is given, and the voltage at the bottom is also given. The problem itself, of course, gives us very simple terminology because they give Q1 and Q2. So because they're all in saturation, so therefore we can say VBE equal to 0.7 volts. And we also assume beta equal to infinity. So therefore we can right now to get from with Q1, let's start with Q1. So VBE 1 equal to 0.7. So this is 0.7. So we got VE 1 equal to 5 minus 0.7 equal to 4.3 volts. And from Q2, we have VBE2 equal to 0.7. And then we have VC2 is going to be minus 4.3 volts, which is minus 5 plus 0.7, right? So this is minus 5 plus 0.7. We get 4.3. So therefore, we can get I1 equal to 4.3 minus 4.3 divided by 20K. So we get 0.43 milliamp, because 0.43 milliamp. So we got that. So now we can go to Q7 and 8. So Q7 and 8 are going to have the same current. So therefore, we got I4. I4 is going to double. It's going to be 2 times 0.43 milliamps. It's going to be 0.86 milliamps. Therefore, we VC7 equal to VC8. It's going to be 5. It's going to be 0 minus 5K times 0.86, which is going to be minus 4.3 volts. Okay, so that's fine, 4.3 volts. And I9, it's going to be same as I1. It's going to be 0.43 milliamps. Okay, and then I11 is going to be same as I9. It's going to be 0.43 milliamps. And we got V11. VC11. VC11 is going to be, so that VC11 is going to be equal to R5 times I11, which is going to be 0.43 times 10, which is 4.3 volts. We got that, and then we can come back to Q3, and for Q3, it's going to have the same current, so we call it I3. We C3. So VC3 is going to have equal to I3 times R2, 8 times 0.43. It's going to be 3.32 volts. And for Q4, we got I4. It's going to be same as 0.43 milliamps. And so I6 is going to be 0.43 milliamps. And then we got VE6. So VE6 is going to be 5 minus 3.6K times 0.43 milliamps. And I have to use my calculator to get the actual number. Let me actually do this, just to give you guys actually correct answer. So it's going to be 5 minus 0.43 times 3.6 go to 3.452 volts. So we got all the problems solved. So here we have the answers actually was from the previous slide. So you can now get the answer. You get all that. Maybe I also go back to talk about example 85. So example 85, looking at I/O is at 10 milliamps, and it determines the required volume of resistor, assume that will be 0.7, kind of 1 milliamps, and neglect the effect of infinity battery. So battery is infinity. So in this case, if we know the above is 3 volts, because battery is infinity, so battery is infinity, therefore IB is 0. So in this case, so I reference will be same as IO, is 10 microamps. And because VBE is 0.7, so we have here 0.7. So this will be 0.7. So right away, we got RE equal to 3 volts minus 0.7 divided by 10 microamps. Remember, this is micro. So you got 2.3 divided by 10 micro. So you got 0.23 megohms. Yeah, that's very big. Or 230 kiloohms. That's that right? R1 is 2 VPE. So that's what we assume the VPE is 0.7. Now, in fact, because the current is so small in the microamps, we like the solution here given is actually 242 ohms. The reason is that when the current is so small, the reference current, the VB is not going to be 0.7. Because when we said 0.7, that's what we get. So what you really need to do is to reflect. So this is wrong. This is totally wrong. Is to look at the equation here is I C equal to IS times E to the VBE over VT. Now here we assume VT is 25 millivolts. Okay, so which means if IC is 1 milliamp, equal to IS times 0.7 over 25, that's milli, that's volts. So remember that difference. So you have IS equal to basically that 1 over E times 0.7 divided by 25 milli. That's what IS is. And this is going to be milliamps. So your actual current IC is going to be IS now is going to be 1 over E over 0.7 divided by 25 milli. That's IS times E to the VBE over VT. So from here, you can find, so IC is given at 10 microamps. So from here, you can find VBE is actually equal to 0.58 volts instead of the earlier volume. So if VB is 0.58, so now you can have this, this should be kiloohms. So you got then you have this VR1 equal to 3 minus VBE divided by 10 micro. That gives you 242 kiloohms. So this is kiloohms. So that's what we get for 8.5. Well, yeah, I did this one. Okay. I think I'll do a little bit more for next lecture because we're running over time. But I'll go through these few examples when we start the lecture in next week. Thank you very much, and I hope you enjoyed it. We'll see you next week. Bye-bye.